Speaker is Chuck Hillman, who was here last year and presented some of the information that he's going to present today. Chuck is a professor at the University of Illinois, and his lab has made major contributions in the area of physical activity, cognitive function, and learning outcomes in children and adolescents. Chuck.
So good morning. I'd like to begin by thanking Art and Pat and their team for having me out today. And just to apologize, my voice is a bit shot. I got some allergy this week, and that's all that's left of it, so you'll have to bear with me. Before me, the speaker's done a nice job of overviewing physical activity in the field as a whole and addressing needs. My work is a bit different. I'm pretty well focused in one area, and that is cognitive health, brain health. And so certainly, I'll let you read through my intro slide, but they did a far better job than I did of introing this area. But basically, we know that there's physical inactivity issues going on in society today. And we know that we're not sort of at the peak. The recent data suggests that these trends are going to continue and worsen. And what I aim to talk about today is what's much less known. That is to say that academic achievement is a hot topic, and it's discussed more and more every year, but sort of the underlying basis for academic achievement isn't very well known. And so several years ago, I collected data in the schools in Champaign-Urbana with a colleague of mine, Darla Castelli, who's now at the University of Texas, and we looked at the relationship between kids' performance on the FitnessGram, which is we went into the PE classes and conducted this test ourselves, and we compared it with their scores on the Illinois Standardized Achievement Test for reading and mathematics. And we found that the number of times the kids fell in the healthy fitness zone and the number on the different tests of the FitnessGram, which is there are 5 tests ranging from a pacer task of cardiovascular fitness to muscle fitness in push-ups and sit-ups or curl-ups, flexibility in a hamstring stretch, sit and reach, and then BMI as the last factor. And we showed that the number of times they passed these tests or fell in the healthy fitness zone was related to their performance on these standardized tests of math and reading. When we broke it down and we looked a bit further, we found that the PACER test, the cardiorespiratory fitness test, was associated with reading and math achievement, such that increased number of laps run was related to better performance. Muscle strength and flexibility were unrelated, and body mass index had a small but negative relationship. And so this is a nice intro because the rest of the data I'm going to talk about will cover one of these 2 areas, either body composition or cardiorespiratory fitness. And so some more recent work I've been doing with Joe Donnelly, who's at Kansas Medical Center. He'll be talking about these data a bit more. But we're working together on a project that he's running in schools where kids are receiving in-class physical activity opportunities or control condition in short bouts. And these data here, if you just look at the bottom graphs, what we're looking at here are relationships between either the PACER test with either tests of attentional inhibition or tests of working memory. And these are 397 children in the 2nd and 3rd grade. And what we're finding are nice relationships between performance on these tests of inhibition and working memory. And not only are they present, but they appear to be disproportionately larger for tasks or task components that require greater amounts of cognitive control or executive control. And so what is cognitive control? Cognitive control is inherent in academic achievement. These are functions that are required for scholastic performance, for vocational performance, for marital health. Pretty much all of the higher order thinking we have in our daily lives is in some way related to cognitive control. While there's various definitions, it can be broken down into 3 different areas. One is inhibition, which includes both attentional inhibition or response inhibition. So this is your ability to ignore distractions, stay focused. You can see where this is very vital to a child sitting in a classroom. Working memory, our ability to hold information in our mind, manipulate it, and then use it when it's appropriate. And finally, cognitive flexibility, which is something we also call multitasking. That's your ability to work on a problem, attend to it, inhibit it, go to a second task, attend to that, execute a response set appropriate for that task, and then inhibit that and go back to the first and back and forth. We do this all the time in everyday life. Unfortunately, we do this while we text and drive and things like that. And so tasks we use in our laboratory are quite simplistic in nature, but very detailed and very data rich. And so here's a flanker task. It's a task of inhibition. And quite simply, whoops, what happened there? There we go. So quite simply, why is it? Center button, there it is. Yep, there we go. Okay, we have multiple conditions where all the arrows point in one direction, and other conditions are called incongruent conditions and congruent conditions, where the arrows point in opposite directions. The task is simple. Look at the middle target arrow and press the button based on the direction the arrow is pointing. But as you can see, in the congruent condition, we're only mapping one response, a right button press. But in the incongruent condition, we have to inhibit the tendency to press the right button and instead press the left button. And we know through years of research that people perform more poorly and have longer reaction times on these incongruent tasks. And so using these data, we looked at approximately 40 kids who are, sorry, Russ, these are cross-sectional data. There's 40 children, 20 are high fit, 70% and above for their age and gender, and 20 are low fit. They're 30% and below for their age and gender. And what we're showing here is differences in brain structure. So these were taken using MRI, and what we image here is the basal ganglia, which is a subcortical structure that's involved in cognitive control and action. And what we see is that regions of the basal ganglia, such as the caudate nucleus, the putamen, and the globus pallidus, all show increased volume in higher fit compared to lower fit kids. And it's interesting because these are the regions that are involved in cognitive control. But the basal ganglia also has a built-in control condition for us in this nucleus accumbens region. This region is not involved in cognitive control. It's involved in affect and reward, how people feel about certain things, how they respond in reward situations. And what we find is that there's no relationship between higher and lower fit kids. And so it seems that we see disproportionate relationships between brain volume and fitness. Now, interestingly, and I don't present the data here, we also show that these fit kids perform better than the unfit kids on this inhibition task. They more appropriately respond, so they're more accurate, and they respond more quickly. And basal ganglia volume appears to mediate that relationship between fitness and performance. Now, other tasks we use in our laboratory are a bit more complicated, but certainly very rich as well. This is a task of relational memory. Relational memory is important because the hippocampus is a vital structure that we have in our brains, and it's the only structure in the brain that continues to have neurogenesis throughout the course of your lifespan. And so, unlike regions for cognitive control like the prefrontal cortex, which are already decaying at the age of 30, the hippocampus actually has the ability to continue to grow and gain strength. And lifestyle factors have been shown to positively influence, actually and negatively influence the hippocampus. And so, for instance, much of the work is in animals, and we show that mice, for instance, that are given exposure to a running wheel have more hippocampal volume, better function in the hippocampus, and have better memory. But specifically, memories tied to hippocampal function, so hippocampally dependent memories. And so here's a task where kids, again, these are 20 different kids, they're all 9 and 10 years old, 20 in each group, sorry, high and low fit. And they're looking at these pipes, as we call them. They're structures that we created in the laboratory, and in one condition, it's just an item task. Have you seen these pipes before? And they either answer yes or no. That is not dependent on hippocampal function. But in another condition, we ask them to create associations between them. Have these pipes co-occurred? Did they occur in the same series? And when you ask an individual to create associations between objects in their environment or with their environment, that's a hippocampally dependent task, to create relationships or associations. And what we find is much the same. Here's the volume in the hippocampus for higher fit kids, and here's the volume in the lower fit kids. So we're seeing a very large increase in volume in this structure in higher fit compared to lower fit kids. When we look at performance, we see that in that item task, which is a lot easier, there's no relationship. But in the relational memory task, we see where the hippocampus comes online, we see the higher fit kids outperform lower fit kids. And again, hippocampal volume mediates that relationship between fitness and performance. Now, this is something that Russ might like a little better. These are new data from from a recently completed randomized controlled trial in our laboratory called the FITKids trial, Fitness Improves Thinking. This is an after-school program that occurred every day after school, in which school occurred for an entire day, so it's 150 of the 170 days of the school year. And kids are randomized either to this physical activity after school program, which occurred on campus at the University of Illinois. They're bussed over, or they're in a waitlist control group. And we had 221 children, fairly equally divided. And they performed every day. Those in the FITKids group performed a little bit more than 70 minutes of moderate to vigorous physical activity following each school day. As you can see, there's efficacy in the intervention because it's basically the same data, but if you look at percentages here, you can see that those in the intervention group increased their VO2 max by about just shy of 6%, where those in the waitlist control group increased by less than 1%. And so we did a sufficient job of increasing fitness in the intervention. We used a flanker task. It was more appropriate for kids. We used fish instead of arrows. Asked them to point in the direction in which the middle fish was swimming. And what did we find? We found that response accuracy increased. Those in the FITKids group were a little lower to start, but they increased almost twofold, as you can see over here, just shy of 8% as opposed to just shy of 3.5%. And so we saw an increase in cognitive control related to inhibition following this intervention. We dug a little deeper. Oh, actually, I guess I'll come back to the brain data in a minute. We used a second task called a switch task. This is a task of mental flexibility where kids had to hold two different rule sets in their mind. In one case, they had to make distinctions between circles and squares, and the other between colors, green and blue. And they went back and forth making decisions about which rule they had to do based on the direction of the arms of the figures, and then implement one strategy over another. This is a much more difficult task. And as you can see, those in the fit group started out, or in the fitness group started out a little bit poorer, but not significantly so, but finished a little bit above, again, not significantly so. And so they had an increase of about 10% in performance on this task, where the waitlist control group had just shy of 6%. And so, here's the data I was looking for. And so in addition, we looked at event-related brain potentials. These are data that are neuroelectric potentials, so it's electricity in the brain that's related to the allocation of attentional resources. The more attention that's paid, the larger this component called the P3 component. And what we can see here, if you just pay attention to the colored plots, you can see that these are change scores for that flanker task and that switch task in the intervention group, the FITKids group, and you can see that they increase the amplitude of this P3 component here and here as well, significantly larger there. Both were significant, but significantly larger for the secondary task, this switch task. And what we find is that they upregulate this P3 response, so they upregulate the amount of attentional resources during task performance. And when you look over at the kids in the wait list, they show very small changes that are non-significant. And so from pre to post over the course of this time, we see an upregulation in the amount of attentional resources, improvements in task performance on these cognitive control tasks. And importantly, I don't show the data because of time. We have other tasks that are not cognitively control related, and there's no relationships there. So it appears to be more selective to tasks that require greater amounts of cognitive control. Now, there's one more piece of this data set. When we compared attendance rate in just the FITKids, so the amount of time they actually came to the intervention, and we looked at changes in this P3 component, we see a nice positive relationship. Such with an increase in attendance, we see an increase in P3 amplitude. We also see a decrease in P3 latency, which is another component, or it's the timing of that component, which is related to cognitive processing speed. And so what we find is that more time in the program is related to faster cognitive processing speed. So they're processing information more quickly, they're allocating more attentional resources, and then we also see that with more time in the program, they're also performing better with higher attendance rate related to better response accuracy on the tasks. Now, here's some other data. it's a little bit different. Instead of a long-term intervention, this is a single bout of exercise. We had children go through a 20-minute bout of walking. On one day they came in, they walked for 20 minutes on a treadmill at a moderate intensity. On another day they came in and they sat quietly for 20 minutes. And then following that, we placed the electrode cap on their head. They did the same flanker task I described, and then they took an academic achievement test. The data that you see here are for just healthy kids, that is no ADHD kids. And what we find is that following the exercise, kids increase their P3 amplitudes, they're allocating more attentional resources. They have faster P3 latency, so they're processing information more quickly compared to the days in which they rested. You can see that it's disproportionately larger in that incongruent condition where there's an upregulation of cognitive control. And these are the maps on the side, which show the same thing. The largest effect is in the cognitive control condition, requiring the greatest amount of control. They improve their performance selectively for that incongruent condition, which I don't show. And when we look at task performance on a wide range achievement test, we see that they perform better. According to the wide range achievement test, this is a full grade level increase in performance for reading. And they also show improvements in arithmetic following exercise as opposed to the day in which they rested quietly, sat quietly and read a magazine. Now, I don't have the data I was looking for, but these actually consist of both typical kids and ADHD kids. We found a main effect such that both groups showed this increase in performance, and so I presented in that regard where I should have found my data with both ADHD kids parsed out. So some other data we have here. From the pretest of the FITKids trial, we found that there's a large number of children who are overweight or obese, unexpectedly large, almost 60%. And we used DEXA measures to get a measure of central adiposity, so basically belly fat. And we compared that with performance on tasks of inhibition and tasks of working memory. And so what you see here are costs of these two aspects of cognition. And so the higher the number, the more poorly they performed. And what we find is that with an increase in abdominal fat mass, we see an increase in the cost to inhibition and an increase in the cost of working memory. So 122 children here who are 7 and 9 years of age. When we look at the academic achievement test again, of wide range achievement test of reading, spelling, and math, we see a very similar effect. Reading, spelling, and math all show decreased performance related to an increase in abdominal fat mass. Now, digging a bit deeper with a different sample of children, we gave them a test of inhibition. This test is a classical test in the laboratory to measure the P3 component. In the first condition, it's called the go condition. They look at, in this case, those pictures of tigers. Occasionally saw a picture of a lion. They press the button when they see that lion. Real simple task, nothing cognitively demanding about it. And then we reversed it. We asked them to press the button every single time they saw that tiger and to inhibit the response when they saw that lion. Now, that is a much more cognitively demanding task. It requires inhibition because we've already built up a prepotent response, and we take it away. And so they go through going tiger, 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 and they get that lion, and they have to inhibit the response. What we found was that obese children, there's about 20 per group, obese children perform selectively more poorly on the no-go condition compared to healthy weight children with no differences in weight. No differences in the go condition. When we look at brain activity, it's pretty striking. When we look at this P3 component, which shifts more frontally in response inhibition tasks, we see that healthy weight children have a nice large amount of activation in order to successfully inhibit the demands of that task. Where obese children have a much smaller P3 frontally than their healthy weight counterparts, suggesting that they're not upregulating the necessary resources in order to perform that task appropriately. So I'm gonna have one last study here. I raced through a little bit to try and get to this. This is our newest data. It was recently published in PLOS ONE and made the rounds to the media, including New York Times last week, 2 weeks ago. And everything I've told you about so far and everything in the literature so far is all about performance. How well do kids perform on tasks? Not are they stronger at attention or stronger at working memory, but how they perform on these tasks. Well, in this particular study, we asked higher and lower fit kids, and I should tell you right now, they're actually replicating this in the magnet, but these are just behavioral data. We asked these kids to come in and perform this task where on the first day, we showed them maps. And these were fictitious maps with fictitious names assigned to them. And they just tapped it. A name would appear in a region. They would tap the region, show that they've seen it, and they would go through. And then we'd test them each time through, and they would have to decide in the study-only condition. There's 2 conditions. The study-only condition, they would tap that they'd seen it. In the test study condition, the name would appear on the side, and they would have to tap the region that they thought was correct. And so they were we gave them a strategy in which they were testing themselves the entire time in which they were encoding. So you have a study only with no strategy or a test study in which there was a strategy. And at the end of that day, they went through it 6 times. You can see that both higher and lower fit kids learned the maps fairly well. there's no differences whatsoever. So the encoding was not the issue. They both encoded the new information. They learned that new information appropriately. Then we asked them to come back a day later. And on that next day, we gave them the maps again. And you can see in the, they had to recall the information in one of two conditions. Either in a free condition where they free recalled, they just had to go ahead and fill in the maps. So they'd click on each one, type in the name. Or an acute condition where all the names are at the bottom, they had to just plug them into the different regions. And what we found was that in the study-only condition, where we gave them no strategy, higher fit kids outperform lower fit kids. So just in their ability to encode and then recall that information on the day of recall, the retention day, 24 hours later, we found that higher fit kids outperform lower fit kids on what's a quite difficult task. In the test study condition, which we gave them all a strategy, we showed that the relationship went away. And as you can see here, when we look at it by recall condition, higher fit kids outperform lower fit kids in the most difficult condition, the free recall, in the study-only condition. During the cued recall, the effect was marginal. In the test study condition, we see a significant effect, but significantly smaller during the free recall. And the cued recall during the test study condition, the effect goes away. And so it appears that learning is actually improved 24 hours later in higher fit kids. There's an association of improved learning in higher fit kids 24 hours later during recall. So to summarize, let's see. Hopefully I provide some evidence that fitness may benefit brain health and academic performance, or at least the neural substrates and behaviors that underlie academic achievement. And fitness has been linked to changes in cognition. And we've shown through many publications now that these changes are disproportionately larger for tasks or task components that require greater amounts of cognitive control. Certainly, I'd advocate that early physical activity experience would shape cognition and its neural underpinnings. And I think, as Russ said, we're just scratching the surface. We really don't know a lot of this. And there's a lot of different areas that we can focus on. And our laboratories branch out in all kinds of different ways, including areas like creativity and whatnot. Excess adiposity is related to decrements in cognitive and brain health and scholastic achievement. But certainly, we don't know the nature of that relationship yet. And this is certainly correlational, and there's probably third-party factors involved. Single bouts of exercise benefit brain health, cognition, and achievement. And clearly, this is a utility that could be used in schools and something that Joe Donnelly will talk about later as being a behavior that we can implement into the school environment to improve performance. And so collectively, our data suggests that time spent engaged in physical activity doesn't detract from academic performance, and that early intervention is crucial towards lifespan health and effective functioning of brain and cognition. So with that, sorry for the speed and the lack of voice, but thanks for your attention.